Okay, welcome to this lesson. This is my second video on the definition, explanation, and equations of simple harmonic motion. In the first video, I explained simple harmonic motion or defined it in terms of acceleration. That acceleration is given by negative of the omega squared, which is the angular frequency squared, multiplied by the displacement of the body. And we have seen that the acceleration is not constant. It is directly proportional to the displacement of the body from the fixed point, which is also called the mean or equilibrium position. And that the acceleration and displacement are both vector quantities. The negative sign shows that the two directions are in opposite. The acceleration and displacement are oppositely directed. Now I want to continue from there in this video by showing you that the angular velocity or frequency is still given by 2 pi multiplied by the frequency, or can still be given as 2 pi divided by the period of oscillation. So which means I can write the equation as negative 2 pi f all squared times displacement. Now you may be asked a question like this. Let's just solve this question before I make more progress. A pendulum bulb is in simple harmonic motion with a frequency of 5 Hz. We have to calculate its acceleration when its displacement is 8 cm. So how do we solve this? Let's write down solution. Acceleration is if I'm asked to find the magnitude of the pendulum's acceleration, means I'm going to ignore negative sign because in this equation, negative sign clearly shows direction. Okay, so I'll ignore that and just take it as omega squared multiplied by my displacement. Now, the units of displacement will be in meters. Most times they'll give you centimeters, millimeters, and therefore, or make sure you convert it to the meters. Now, omega is given by 2 pi multiplied by frequency. We're going to take pi this time around. Most times will be given as 22/7. That will give me 2 multiplied by 22/7 times 5. My frequency was given as 5 hertz. So with my calculator now, I can quickly evaluate that. That's 2 times 22 times 5. That gives me 88 times 5. Sorry, 44 times 5 rather. 44 multiplied by 5 divided by 7. Okay, so I have 44 multiplied by 5 multiplied by 5 divided by 7 divided by 7. That gives me 2.8 2.85, or let's round it off to 86 radian per second. That gives the angular frequency. So the magnitude of the acceleration will now be 2.86 squared. Remember to square that, multiplied by 0.08, because we must convert 8 centimeters to meters by dividing by 100. So I have to square that. 2.86 squared multiplied by 0.08 will give me my final answer. So the acceleration of the body, that is the magnitude, is 0.65 meters per second squared. Okay, that's how we use that this equation of simple harmonic motion to calculate the acceleration. Sometimes we're given the angular frequency and the displacement. I'll be required to find the acceleration. Just to make that this up directly, that is without giving you the frequency, they'll give you the angular frequency, or we'll be given the acceleration and displacement to find the angular frequency. So that in that case, angular frequency squared is acceleration divided by displacement x, and then angular frequency now taken as the square root of acceleration over what? Displacement. So it may be the question may come in that way in exam, and you ask to find that you need to do that quickly. Now we need to understand again that not all oscillatory motions are simple harmonic, but all simple harmonic motion are oscillatory motion. I take it again. Not all oscillatory motions are simple harmonic, but all simple harmonic motions are what? Oscillatory motion. How do we show that? Let's see an example here. Let's say we have two planks that are inclined like this. See how the two planks are inclined to each other. Let's say this is horizontal. Okay, so this may be the same, that is the angles of inclination for the two planks. This plank 1, plank 2. And there's a ball here that is free to roll down along the smooth surface of this plank, assuming that there is little or no frictional force between the ball and the surface of the plank. Now this ball can roll down to this point and then move up the other plank and then comes down again continuously. Can we prove that the motion of this ball from the first plank down up the second plank and then down to the first plank continuously, can we show that the motion of this plank is not simple harmonic? Now, first of all, let's look at the acceleration of this ball as it moves down this plank and move up the second plank. The acceleration is given by g sine theta. We can use the ideas of dynamics of motion because if the frictional force is negligible, then the components of the weight of this ball, the weight acts vertically downwards, of course, you know that. The component of the weight of this ball acting along the plane is your mg sine theta. Mg sine theta component is what is actually responsible for the motion of this ball down the plane. So that can be equated from Newton's second law. Resultant force mg sine theta is equal to ma. From Newton's second law of motion, F is equal to mass times acceleration. So m cancels m. You can now see that the acceleration of the ball down the plane is given as g sine theta. Now, from the definition of simple harmonic motion, the acceleration of the body in simple harmonic motion ought to be directly proportional to the displacement of the body from the fixed point. That is to say, I've said earlier, I've also stressed it, that acceleration must not be constant. So seeing here clearly that the value of g is constant for a particular location on the earth surface is roughly 10 meters per second squared, and the angle of the slope, angle of inclination of the plank is constant. This is not changing as the ball is moving up and down along the two inclined planes. So if this is kept constant at 30, you can see that this is constant, the angle theta is constant. That shows that the acceleration is constant and the body's motion is not simple harmonic motion. It appears to be a kind of oscillatory motion, to and fro motion. How about the case of two footballers passing the football towards each other? You have this footballer, the ball gets to him and he kicks the ball to his friend standing on the other side facing him, and continuously they keep pushing this ball to each other. You notice that they may not maintain the same acceleration. They may not even be a center of oscillation. You know, this one may kick it with a speed that is even greater than this, or the ball may accelerate from this boy A here towards boy B, and boy B may apply a small acceleration or even move the ball with a constant speed. So though this ball is moving to and fro between these two boys or two footballers, but the motion of the ball is not simple harmonic motion because number one, we cannot clearly identify the center of oscillation. Number two, the ball can even move at some times with a constant speed. You know, the speed ought to vary, or with a constant acceleration, the acceleration ought to vary. So that's why we cannot clearly pinpoint that the motion of this ball to and fro between these two boys is a simple harmonic. All right, so and many more, So just understand that most oscillatory motions are not a simple harmonic. So let's still look at this way again. That if we must know, or if the motion of a body is simple harmonic, it means that number one, the acceleration must be proportional to the displacement, directly proportional to the displacement of that body from the fixed point. That is, A must not be constant, and that if I'm going to show this again graphically, because sometimes we need to show graphically the variation of the acceleration of the body, you know, how does it vary with displacement from the fixed point? Let's just quickly show graphically the variation of the acceleration of the body A with displacement x. Now let's say this point O, where the two axes cross, is called the center of oscillation. Now the ball can swing from this mean or equilibrium position to one extreme point. We call that x naught. This x naught, the distance from the center of oscillation to point x naught, we call that the amplitude. Of course, I'm going to come to that in the next video. Amplitude is defined as the maximum displacement of the body from the mean of fixed or equilibrium position. Okay, so let's say this one extreme point A, and then the ball goes back to point O, goes past point O to another extreme point B. I can call that the distance from point O to this point is minus x naught. This time around, I'm using x naught as the amplitude. In some textbooks, some authors use A for amplitude, while some use the uppercase letter A for amplitude. So here I'm going to be using x naught. Sometimes I can alternate between that and the uppercase letter A to denote my amplitude of oscillation. So let's say that the maximum oscillation is at this point. Of course, the maximum acceleration is given by omega squared times x naught. Okay, that's positive. And acceleration can also be on the other side, negative. Negative omega squared times x naught. Okay. We just need 3 points to be able to draw this sketch or draw this graph. Let's take 3 points. Number one, let's say the body is x, the displacement is equal to 0. That is when the body is at the center of oscillation. What is acceleration? Remember that this is given as minus omega squared times x. So that means that acceleration is equal to minus omega squared multiplied by 0. That gives you 0, since displacement is 0. So I come here now. When the displacement is 0, the acceleration is 0. I'm going to plot the origin of my axis. Okay, so now let's move to another point. How about when the displacement is equal to the amplitude x naught positive? That is when the bulb swings from point O to point A, positive displacement x naught. It means that the acceleration A is minus omega squared times, and replace this my x with x naught. That gives me this. So that is minus omega squared x naught. I'm going to plot that here. That is when my displacement is x naught. Bring this down. Then my acceleration was equal to minus omega squared x naught. Take this across. So where the two of them meet, I'm going to plot that point. Then lastly, suppose the displacement x is equal to minus x naught. Let's say the bulb has swung to the negative, to the other side of the center of oscillation, that is point B. And remember that we give that negative displacement. Okay, so we see that A acceleration is going to be equal to minus omega squared multiplied by minus x naught. Okay, so my x naught is negative. Negative multiplied by negative gives me positive omega squared x naught. Okay, I come here now. I bring this one out, trace this out, take this up where the two meet, I plot. So with all the other points I want to choose, will definitely fall on the straight line I'm going to draw. So these 3 points are sufficient for me to draw my graph showing the variation of the acceleration of the body in simple harmonic motion with displacement. So you can see it's a straight line graph, meaning that simple harmonic motion is a motion of a body along a straight line. That is to say, it's a uniform motion of a body. Uniform motion of a body about a fixed point. That is to uniform motion of a body about a fixed point. Uniform. If it was non-uniform, the graph would have given us a curve. It would have given us something like this to show that it's actually a non-uniform motion, or whatever it is, a curve. As long as the graph is straight line, means it's a uniform motion of a body about a fixed point. How do you deduce from the graph that the motion of this body is simple harmonic? Because the acceleration of a body in simple harmonic motion is still defined as this omega squared x. Now, it means that number one, the graph must be a straight line graph that passes through the origin. For the fact that the graph is a straight line graph, it means that the slope of the graph will be a constant. Remember that all straight line graphs have a constant slope. Remember the equation of a straight line graph, y equals mx plus c. This is a general equation of a straight line graph where m represents the slope of the graph, and this m is a constant. It's not a variable. It's a numerical constant. So if I find the slope, maybe taking 2 points on this graph, let me call this point 1 and call this other point point 2, and then I place my slope triangle this way. I draw my slope triangle like this, and then find my change in acceleration, that's along the vertical, along the horizontal change in displacement. I'm going to have my slope as equal to change in acceleration point 2. Come to point 2, that is a2. A2 was minus omega squared x naught minus, what was my a1, or point 1? That's a1 omega squared x naught. Okay, divided by, what is my x2? Because I'm going to have change in acceleration over change in displacement. That's how we define the slope. So that will give me x naught minus x naught. Okay, because this is positive x naught, this is negative. So minus x, that gives me negative 2 omega squared x naught. That is minus omega squared x naught minus omega squared x naught over 2, what is that? X naught. So this will cancel these two. X naught cancels x naught. So you can see that my slope comes out as minus omega squared. So the slope of the graph is negative because of the orientation of the graph. Remember in graphs, when the graph is oriented like this, it has a positive slope. And when it's like this, you see it has a negative slope. So that means that the graph must be a straight line so that the constant, the slope will be a constant since this omega squared represents the slope and it's a constant. Then number two, the graph must pass through the origin. To pass through the origin means that A must be proportional, directly proportional to what? To x. So these are the two features we can count on or deduce from the graph if the motion of the body that has this acceleration displacement graph is going to be simple harmonic. Number one, the graph must be a straight line so that the slope will be constant because this our constant is gotten from the slope of the graph. So if the graph was a curve has a variable slope, then this will not agree with this statement, with this equation. So the graph must be a constant so that this will be constant. And number two, the graph must start from the origin. If the graph were to be like this, that it will not mean, it will no longer hold or be true that the acceleration is directly proportional to the displacement. We can just say that the acceleration depends on the displacement. It's not directly proportional to the displacement. Okay, so in the next video, we shall look at more terms, define some terms, and then solve more problems in simple harmonic motion.